So in 3.5, we are going to be looking at rational functions. And this is kind of divvied up into 2 days. First day, we're going to look at how to find certain objects with the rational functions. And the second day will be actually drawing the graph. So the graphs can look like this. They don't all look like this. But basically, a rational function is where you have a polynomial all over a polynomial, okay? And it can be anything. Remember, polynomials can be a number. It can be an x. It can be 2x. It can be x minus 5, x squared, etc., etc. So we have 2 polynomials. Now, normally what you're going to have is you're going to have something with the x, with an x in the denominator of a fraction, in order to get a graph that looks like this, okay? So just let me point out a few items of note. These curves here, these are actually the graph parts. The blue lines are what we call asymptotes. So this line right here is a horizontal asymptote. And it, for this particular graph, it's y equals 1. Okay, I'm having problems with my focus. I'm just going to get rid of that light. Now, these other 2 lines here, these are vertical. Asymptotes. Okay, and they're located at x is 2. And x is negative 2. Now we also have intercepts. We have x-intercepts. We have y-intercepts. Sorry about that. We have x-intercepts here and here. We have a y-intercept there. So what we're going to do is we're going to go through and figure out how to find these asymptotes, these intercepts, and then next time we put it all together. Okay? So as with as with rational functions we did earlier, we looked at domain. So the asymptotes oftentimes go with the domain, but we're going to go ahead and find the domain just to get a little practice here. So we cannot have 0 in the denominator of a fraction. So x is 2. Would be what gives me 0. So therefore, my domain, and depending on, again, how you're asked to identify it, x cannot be 2. For this equation here, x squared minus 4 is 0. Then I factor. And what I get now are, I get 2 values for x that x cannot be. So x cannot be negative 2, comma 2. So it cannot be either one of those. And you'll see, hopefully, when we start doing the asymptotes, how this kind of goes together. Because basically, for a vertical asymptote, it's the value that x cannot be. We cannot substitute it into the equation and get a y value. So we create these borderlines. All right, so then that's one thing we need to be able to find. The other things are your intercepts. X-intercepts, y-intercepts. Now, y-intercepts, let x be 0. X-intercepts, set the equation equal to 0 and solve for x. So first, we're going to do the y-intercept, as it's, the least painful of the 2. So r of 0 is 3 times 0 plus 2 over 0 minus 2. R of 0 is 2 over negative 2. So r of 0 is negative 1. So that's your y-intercept. Now your x-intercept, and sometimes you can have more than one. What we're going to do is we're going to solve 3x plus 2 over x minus 2 equals 0. So we have to eliminate fractions, so we can multiply both sides by x minus 2. And hopefully what you notice is we're just left with the numerator equal to 0. So we subtract 2, divide by 3, so x is negative 2/3. So my x-intercept is negative 2/3, 0. Okay, so these go with this particular equation. For example, 4, same process, y-intercept, r of 0 is 0 squared plus 4 times 0 plus 3 over 0 minus 5. All those zeros go away, and I'm left with 0, negative 3/5. So I'm going to have to roll over here. Now my x-intercept and in this case we're going to have 2. We're going to set the equation equal to 0, solve for x. So what I'm going to do is I'm going to multiply both sides by the x minus 5. And what I'm left with is, again, the numerator equal to 0. Always true. Always true. So I must factor. Factors of 3 that add up to be 4, 3 and 1. So x is negative 1 or x is negative 3. So for this one, I have 2 x-intercepts. So y-intercept, when you look at the y-intercept, when I put 0 in for my x's, everything with an x goes away. When I do my x-intercepts, what I'm doing is I'm finding the 0 in the numerator through this process. Okay, so that's 2 items you're going to have to be able to find to graph the equation. Now let's talk about the asymptotes. So a vertical asymptote is a vertical line on a graph where the equation is undefined. And again, it's oftentimes the same as the domain. And it's the x value or values that gives a 0 in the denominator. So your instructions would be to find the vertical asymptote for each of the following, and then identify any holes if they exist for the graph itself. So we'll talk about holes here in a second. But in this case here, for this particular rational function here, I set the denominator equal to 0. Again, it's the same as the domain, and so therefore I have kind of this borderline at x is 1. Which means if I choose x for 1, I do not get a y value. So there are no points to plot at x is 1. That's basically the purpose of the vertical asymptote, is to give you boundary lines. The graph will not cross here. It's not continuous. Okay? For this second one, again, it's kind of what we found earlier for the domain already. So we solve this. We factor. So x is -2 or x is 2. So I create an asymptote at x is 2 and one at -2. So again, borderlines, values where x is undefined. So far, we haven't had to worry about holes. Now, when we talk about holes, they come from equations where we have common factors. Okay, so I didn't really truly have to factor either one of these. I mean, I could have factored this first, but it's fine. I did it second. But for here, we're going to go ahead and factor, since we do have quadratics in both the numerator and the denominator. So, given this scenario, we can cancel common factors. So what we are left with then is x plus 3 over x plus 7. So my vertical asymptote is at -7. So I didn't really give you enough room here, but at any rate, it's at -7. And then I have a hole at x is 3. It's what would give you 0 here. So at x is 3, when we do graph one of these, you'll have a hole. Okay? So the main thing right now is to get the vertical asymptote. If you do come across equations that can be factored, or that's where you need to cancel out common factors, do it, and then your hole would be at the value that would give you 0 in the factor itself. So that's your vertical asymptotes. Now the horizontal asymptote, again, it's a horizontal line like the one I showed you at the beginning. Okay, right there. And it's the line oftentimes that the y value approaches, but will never equal. Okay. Now, the horizontal asymptote, you've got two possibilities. They involve the degree of the numerator and the degree of the denominator. So the first possibility, if the degrees are the same. So if the degree of the numerator is 1, and what we mean by degree is the power, okay? So x squared has a degree of 2, x cubed degree of 3, etc. But if we have 2 in our rational function, if the degrees are the same, what we do is we take the two terms with the highest power, make a fraction, and cancel the x terms. And that would be our number of our horizontal asymptote. Y equals 1, 2, 3, a half, whatever. The other possibility that we're dealing with is the degree of the numerator is less than the degree of the denominator. If this is the case, then the horizontal asymptote is pretty much the x-axis, or y equals 0. Okay, so let's look at an example of each one of these. So this is the possibility 1. We have degree 1, degree 1. So these are the same. So what I do is I take x over x, and don't forget those are both 1s. I cancel out the x's, so my horizontal asymptote would be y equals 1. You know, and if we just had, just off to the side here, I know sometimes this is confusing because of the no numbers out here, but they're ones. Don't forget they're ones. If you had 2x plus 3 over x minus 1, the degrees are still 1. So this would be 2x over x. Cancel out the x's, excuse me, y. And so y would be 2. So that's how you would do that. Now the other one, a possibility, is when the degree of the numerator is less than the degree of the denominator. In this case, the degree is 1. Down here, your degree is 2. So this is the case where it's just an extension of the x-axis. That's what y equals 0 is. Okay. So we'll do more practice as we move on. We will wait on graphing until the next one. And so that's it. So we'll end it here.